let's say I want to make some pancakes. And I've got a recipe for pancakes, and I'm lazy, I'm a bachelor, so I'm going to use a pancake pre-made mix. I'm not going to make it from scratch. Screw that. It takes too much work. They never turn out the right way. So let's just use a pre-made mix. Let's say for every one pancake I want to make, one pancake, I need 1/2 of a cup of the mix, and I need 1/4 of a cup of milk. All right. Now I ran to the store. I got a ton of mix. I have on hand 12 cups of the mix. But I forgot to pick up milk, so I'm just left with what's in my fridge. And in my fridge, I only have 4 cups of milk. So with this in mind, how many pancakes can I make? Well, this is great. We could put this into the same stoichiometric ratios that we've been working with. So let's go for every 1/2 cup of mix plus 1/4 cup of milk. I'm going to get 1 pancake. And I want to know how many pancakes can I make with this material? Well, 4 cups of milk and 12 cups of mix. If I want to convert cups of mix to pancakes, I just go, hey, I've got 12 cups of mix, right? 12 cups of mix times, I want to go from mix to pancakes. Let's say PC for short. For every 1 pancake, I'm going to use 1/2 of a cup of mix. That's 0.5. 12 divided by 0.5. Well, geez, guys, it's 24. I can make 24 pancakes with that much mix. It's a lot of pancakes. Feeling hungry. How about the milk? Well, I've got 4 cups of milk. How many pancakes can I make with that? I go from milk to pancakes. Well, for every 1 pancake, I'm going to use 0.25 cups of milk. How many is that going to be? Well, that's going to be 16. 16 pancakes. 4 divided by 0.25 is 16. Oh my gosh, I cannot spell today. Pancakes. Pancakes. So I can make 16 pancakes with that much milk. I can make 24 pancakes with that much mix. So how many pancakes am I going to be able to make? I'm a pretty hungry guy. I could probably eat 30 pancakes if I had them. So I'm going to make as many as I can. Well, if I mix all of this stuff together and make as many pancakes as I can, I'm only going to make 16 pancakes. And I'm going to be left with some cups of mix left over. After making 16 pancakes, well, that means that there were 8 pancakes that I could have made. 8 could have beens. And we can mourn the loss of those later, but how many cups of mix would I have saved there? Well, I would have saved 4 cups. That's just doing a little bit of math in my head. But the point here is I'm limited by the amount of milk that I have on hand. My milk here is my limiting ingredient. And chemical reactions are going to be the same way. When we do stoichiometry, we're not always going to have the exact same amount of stuff. So if we do some reaction, like let's start with a simple one. Let's say H2 plus O2 making H2O. And if we balance this, we need to put a 2 here and a 2 here. Great. Let's say I've got 10 grams of H2, and let's say I've got 50 grams of O2. How much H2O am I going to be able to make? Well, we can calculate that. We can figure that out. First off, we need to do our regular stoichiometry. We need to start there, right? We need to figure out our molar masses for these. For H2O, our molar mass is 18 grams per mole. For hydrogen, it's going to be 2 grams per mole. For O2, it's going to be 32 grams per mole. Now, right at the outset, you might think, well, there's less hydrogen, there's fewer grams of hydrogen. That's probably going to be our limiting reactant, right? Well, not necessarily. See, the way we do this, the way we figure out this limiting reactant is we need to convert everything into moles because the amount of mass that we have here does not matter to the chemical reaction. It matters to us because this is the only way we have to measure an amount of a substance. We can measure this in grams. Technically, these would be gases. We would measure them in liters, but for now, we're just measuring in grams. We can't measure a number of particles. We can't measure that directly. So we have to convert from grams into a number of particles. And for each one of these, we're going to be able to do that. So let's make a little barrier here so we can do our calculations off to the side because I'm running out of my page here. So hydrogen, let's start with hydrogen. Let's do that in blue. So I've got 10 grams of H2. I don't know, how many moles is that going to be? So grams to moles, it's going to be 2 to 1. That means I'm going to have 5 moles of H2. Okay, so let's put that back over here. I'd say I've got 5 moles of H2. Now let's do O2 in red. I've got 50 grams of O2. 50 grams of O2. And I need to convert that into moles, so grams to moles. And so it's going to be 32. 32 on bottom, 1 on top. And that one I can't do in my head. So let's go 50 divided by 32. Okay, that's 1.5. 1.5 moles. So now I've got 5 moles of H. I should write in the talk. I've got 5 moles of H2 and 1.5 moles of O2. So now what's my limiting reactant? Well, now it starts to look like it's the O2. Even though we have more mass of oxygen, we have fewer particles. We have fewer physical particles of oxygen that are going to be able to react. But we're still not done. Because just like in this recipe above, it wasn't just 1 cup of mix and 1 cup of milk. It was half a cup of mix and a quarter cup of milk. They didn't combine in even proportions, and neither do chemicals. Neither does this reaction. For every 2 hydrogens that I use 1 oxygen. So we're going to need to figure out how many moles of H2O each one of these could make, okay? So when we're trying to figure out the limiting reactant, we're going to do all of our same previous steps where we're going to find the number of moles of each of our reactants, and then we're going to convert from that number of moles to moles of our product. And then whichever one is smaller, that's going to be the amount that we would actually make. So let's figure that out. I've got a blue, I've got a red. Let's go with blue hydrogen. We've got 5 moles of H2. And I want to know how many moles of H2O is that going to be? So I go from H2 to H2O. And for every 2 moles of H2, I'm going to make 2 moles of H2O. So that's an even proportion. So I'm going to get 5 moles. This says 5 moles of H2. How about the oxygen? We've got 1.5 moles of oxygen. Now I need to convert that. Let's move this a little down. So convert that from O2 to H2O. Well, for that, for every 1 mole of O2, I'm going to get 2 moles of H2O. And so 1.5 times 2, that's going to be 3 moles of H2O. All right, 3 moles. So if I use up all of my hydrogen, I would make 5 moles. If I use up all of my oxygen, I would make 3 moles. So how many moles of H2O am I actually going to get? How many moles am I actually going to get? I'm going to actually get 3 moles. Because once I hit 3 moles of H2O, I run out of O2. And then if I was doing this in a container, which why would I? This would be explosive. This would cause the container to shatter and go everywhere. But if I was doing this in a container, after I used up all of my oxygen, I would actually have a container that has some hydrogen left over along with a bunch of water vapor. So this is what we call a limiting reactant. In this reaction, my O2 is my limiting reactant. And so our last step here, just like we were doing before, is going to figure out how many grams of H2O am I going to have. So let's figure that out. Let's bring that over here. I've got 3 moles of H2O. I'm going to convert that from moles to grams. It's going to be 18 over 1. So let's pull out our calculator and do that. It's going to be 3 times 18. 3 times 18. That gets us 54. So we get 54 grams of H2O. Okay, so 54 grams of H2O. So that's the gist of finding the limiting reactant. I just threw a lot of information at you. So let's do another practice problem just so we can get a better hang of this. All right, here's another example. I've got a solution of copper 2 chloride, and I want to get that copper out of it. I know I've got 150 grams of copper 2 chloride dissolved in a solution, so I'm going to throw some aluminum in there, and it's going to have a spontaneous redox reaction where the aluminum will replace the copper, and I'll get pure copper metal falling out of the solution. Now, my goal is to get all of the copper out, and I'm wondering, I only have 45 grams of aluminum on hand. Is that going to be enough? So I can figure that out by figuring out my limiting reactant. Just like every other stoichiometry problem, my first step is to figure out my molar mass. So let's go to a periodic table and let's find aluminum's molar mass. We can go here, boom, aluminum, that's 26.98, so it's going to round to 27. So we got 27 grams per mole. All right, and then copper 2 chloride, and here, let's do a trick here. I already Googled it. Copper 2 chloride, you can just search copper 2 chloride molar mass and you get the molar mass. Now that we know how to calculate it, save some time and look it up. So 134.45, let's round that to 134.5 grams per mole. Tons of rounding there. All right, and then copper, back to our periodic table. Whoop. Find copper, and that's just going to be 63.5. Let's put that 63.5 grams per mole. Great. So now, our first step, if we want to figure out the limiting reactant here, if we want to figure out how many grams of copper I'm actually going to make, we need to find the moles of aluminum and copper 2 chloride. That's our first step here, okay? So we're going to find the moles, convert grams to moles. I'm going to do all my math outside of this box so we can keep at least a little bit organized. So let's start with our aluminum. We got 45 grams of aluminum. We need to convert that to moles. So we're going to take our molar mass, grams under moles. It's going to be 27 over 1. And so when we do that calculation, we're going to take 45 divided by 27. That gets us 1.6, well, around a 1.67. 1.67 moles of aluminum. And now we need to figure out how many moles of copper chloride do we have. Let's put that in, let's do a nice little turquoise here. So that's kind of the color of copper 2 chloride. So we've got 150 grams of CuCl2. And I'm going to go from grams to moles. So that's going to be 134.5 to 1. All right, and then let's do that math. It's going to be 150 divided by 134.5. It's going to give me 1.12. We'll round to 1.12. Great. Now, what's going to be my limiting reactant? We might be quick to say, well, it's going to be the copper 2 chloride, right? But we still have this stoichiometric ratio here, right? We need to now convert from moles of aluminum to moles of copper, and then moles of copper 2 chloride to copper to see which one of those is less. Because this is not going to cut it. So I need to take this one first, times my moles of CuCl2, so that we can get rid of this CuCl2 right here. And we need to convert to copper. So what's that ratio going to be? I've got 3 CuCl2 for 3 coppers. Hopefully by now you're really seeing why we need to balance these reactions. So that's going to be an even ratio. So according to this guy, I'm going to get 1.12 moles. Okay? So it's going to be 1.12 moles. So then let's do the aluminum. So now to get rid of my aluminum, to go to the copper, you look at this ratio, 2 to 3. So there's 2 moles of aluminum for every 3 moles of copper. So I'm going to take that 1.67 times 3 divided by 2. I end up with 2.5. So that's 2.5 moles of copper. So then what's going to be my limiting reactant here? Well, CuCl, the 150 grams of it, makes less copper than the aluminum would. So that means my copper 2 chloride is going to be my limiting reactant. So this guy This guy is my limiting reactant. Limiting reactant. Great. And so now we need to convert from this number of moles to grams of copper. Our lower number is our true amount, because once we run out of that copper 2 chloride, our reaction stops. So this number is now meaningless. We don't care about it anymore. We only figured it out to figure out what was the limiting reactant. That's not there anymore. That's not gonna be true. We don't use all of our aluminum. We're gonna have some aluminum left over. So now let's calculate the number of grams of copper we're gonna have. With 1.12 moles of copper, we need to convert from moles to grams. And that's going to be that 63.5. So we can do that calculation. We get 71.12. And that is our final answer. 71.12 grams. All right, let's try one more example to really make sure we've got this down. So here's a nice complicated reaction to really drive this home. I'm going to start with 1,200 grams of copper 2 chloride and 2,200 grams of sodium bicarbonate. I'm going to be trying to make some copper carbonate, which is a very nice pigment, and I'm going to need to figure out how much CO2 I'm going to produce as well, because CO2 in high enough concentrations is going to be poisonous in the air. So I need to make sure I'm not going to make too much. So as I go through this reaction, I'm going to calculate both of these. I want to figure out how many grams of both of these I'm going to have. So CuCl2, first thing we're going to need to do is convert to moles, same with sodium bicarbonate, and then we need to figure out our limiting reactant. So just like always, let's start by finding our molar masses. All right, we've got all of our molar masses figured out. Let's draw a line so we can keep all our data above this line, and we'll do all of our calculations below that. So first, let's find the moles of copper 2 chloride. All right, and then we need to figure out our number of moles of sodium bicarbonate. All right, so we've got our moles for both of these now. So what's our next step? Do we need to convert them both into both of these products? No, we just need to pick one. In order to figure out our limiting reactant, we just need to pick one of these and convert to moles of that to find that limiting reactant. It's going to be the same for both. So let's use the copper carbonate. So let's go from moles of CuCl2. Let's go from CuCl2 to CuCO3. And so that's going to be a 1-to-1 ratio. So we're going to make 8.9 moles out of the copper 2 chloride. All right. And then let's go from 26.1 moles of sodium bicarbonate, NaHCO3, to copper carbonate. And so it's going to be a 2-to-1 ratio. So 26.1 divided by 2. It's going to be 13.05. So then what's going to be our limiting reactant? Our limiting reactant is going to be my copper 2 chloride. So now these numbers don't matter. We do not need to worry about them. We're going to have 8.9 moles of copper carbonate being created. So now we can calculate how many grams of copper carbonate we have. Okay, let's do that. So we're going to go 8.9 moles CuCO3. Then we're going to go from moles to grams. And that number was 123.6. Okay, so we know we make 1,100 grams of CuCO3. So that's one of our answers. But then we need to know, how many grams of CO2 do we make? How do we figure that out? Do we have to do all of this work over again? No. Our limiting reactant is still copper 2 chloride, and it's still just going to be 8.9 moles. So I'm just going to use that same final number. I'm going to make sure I've got the correct moles of CO2. So let's do that. Let's do that in brown. Let's go 8.9 moles of copper 2 chloride times, we're getting rid of copper 2 chloride. We're going to CO2. So what's our molar ratio between those? Well, that's 1 to 1. Great. So that means I'm going to create 8.9 moles of CO2. And now I can calculate the grams of CO2. I just do that right away. I'm going to go from moles to grams. It's going to be 44 over 1. And so 8.9 times 44. It's going to give me 391.6. 391.6 grams. So I'm going to make 391.6 grams of CO2. So there's both answers. So now we should know how to calculate a limiting reactant in order to find the grams of any number of products for any reaction.